Like she said, my name is Parfait, and I come from the University of Texas in San Antonio. I study civil engineering, and I will be presenting to you my research that I conducted in the summer, which is study the cracking behavior of high-strength steel bar in concrete slab. So, just by a show of hands, how many of you walk around and have seen something like this? That's pretty much everybody in the room. So, what if you see these cracks is something that we know every day. So what if we take these cracks and we put it on, you see something like this. So it's very not good. So studying the behavior of cracks and how the bonding of steel is happening with concrete is very important because we try to avoid all these failures. And this is the Parfait Canyon Bridge. It's one of the bridges here in the coast of California, and it was demolished about 5 months ago just because of excessive cracks that were developed. Just an agenda of what I'm going to go over. I'm going to give you some introduction, background information, and the experimental program that I conducted, and also the methodology, the result, and the conclusion, and some future discussion that will be happening. So the first question you're wondering, what is a high-strength steel bar? A high-strength spiral steel bar. So by definition, a high-strength spiral steel bar is just a bar that has a yield strength of 72 KSI. By that, what I mean is, in order for you, if you have a bar, let's say this is my bar, and in order for me to create any permanent deformation on it, I need to pull on it with a force of 72,000 pounds. That's just different. And these are the high-strength spiral bar that I analyzed for my research. They're very current and new type of steel bar that are still under development. So about steel, if you're in engineering or material science, at one point you've seen something like this, but if you're not, I'll try to go over. Steel has relatively two types of behavior. It has an elastic behavior, which you see on the first region here in the orange, and also have a plastic behavior. So as we analyze our members in steel and concrete, this graph is really important to our experiment result. And what I want you to take away, just remember the elastic region and how the shape of this graph looks like, because that's what's going to determine and how we're going to analyze our results. So there's a really high demand that's been increasing rapidly for the high-strength design because we're trying to design very big, large structures. So engineers are looking at why not use high-strength bar instead of using our regular bars so that we can be more efficient in how we design. And also, there's very limited data in how to use high-strength steel bar in conventional design. The data that exists a lot on high-strength steel bar has been geared more to earthquake engineering because we have a lot of earthquake hazard that happens. So we're trying to focus more on that and keep the conventional design for the regular bars. And also, this research is personal for me because where I come from, the Democratic Republic of Congo, as growing up, there was a lot of crackings and failures that happens around where I grew up, and people didn't take much attention for it. So for me to do this type of research and look into it is very personal also. So the maximum allowable crack width that was set in about 1971. So when you look at, as you design, you run into your calculations and number. The interior exposure crack width allowed is about 0.016 inches, and that's for interior, and for exterior it's about 0.013 inches. And the reason why, back in the day, they didn't have a lot of experiment and data available to analyze all this, and the number one reason that the literature gives us for these measurements is because of aesthetics. So when you look at the shape cracks, if it's very big, your eyes are like, okay, this is a problem. But so the engineers try to minimize to these numbers, and these numbers have been standardized since 1971. And also, the research literature tells us that as you increase the yield strength of steel bars, you run into problems because the strength is higher and you need more good bonding with the concrete, so you run into wider cracks as you design. These bars that I study, there are 3 current methods that are made for high-strength steel bar. The first one is cold rolling, microalloying, and the last one is quenching and tempering. These bars that I analyzed they're used by cold rolling, and this is a picture of these bars as you see here. So the cold rolling is basically as the molten iron is going into this process, you have this die that pushes it into it to change the microstructure of the steel and basically compact all the microstructure inside and keep it together to increase the strength and also maintain the elongation. But the problem is, as you do that, you lose this flexibility and ductility of the steel, which is a big problem in design because we want our material to be flexible. So I'll go for my experimental method. We really wanted to look at what are the mechanical properties and performance of this high-strength spiral bar in concrete, because if we can know how they behave, then we can study how it's going to change our design. So here, our methods, we had 8 concrete slab. 4 of the concrete slab we analyzed, we had regular bars and high-strength bars. So 4 slab were reinforced with regular bars and 4 slab were reinforced with the spiral bars. And we analyzed 2 types of bars, and the diameter was 5/16 and 3/8 for one. And our variables that we looked at was the applied load, the crack width. We also look at the strains and the deflection in terms of drift ratio, how we were applying the load. We also had 100 square elements to help us do our digital imaging correlation. So what we did is, as we were testing the material, every second we'll take a picture of the material as it was deforming so that we can also use that to analyze the cracking behavior. And we take those numbers into that MATLAB to do our data analysis. And a big component of our experiment is the monotonic tension test. And so what that means is we're going to load the bar in the middle. So mono, just at one point, we apply the load at one point in the middle, and we're going to study the cracking behavior of this bar. So remembering how that first graph that I showed you, our first experimental result that we saw for the first type of bar, it's pretty similar. And I'm going to mark out the point that the first red dot that you see there, that's when we saw our first flexural cracking, as we were applying the load monotonically in the middle. And also we saw our first longitudinal reinforcement yield, and that's basically when the bar started elongating, and the bar fractured about at this point at the plus sign. That's where we saw the bar inside the concrete fracture. And this is the same thing. We also saw the same thing happening for the 3/8 bars. And this is what it looked like for the 5/16 when the bar inside cracked. And for the bigger bar, it looks something like this. So you can kind of see that the bigger the bar, the wider the cracks, which is the same pattern that keeps continuing. And when we look at our regular bars, it's more different because the difference here is because the applied load that we're able to apply on these bars were higher, because the regular bar are still flexible, so you're able to extend it to its maximum capacity compared to the spiral bar where because of the co-rolling process, the flexibility decreases. And this is what it looked like at the end of the testing before we could unload it, our testing experiment. And these are the histogram showing you the crack width and the numbers of cracks that we saw. So looking at these first 3 here for the spiral bar, you can kind of see that we have wider cracks comparing to the regular deformed bar. And that's telling us that the pattern is still continuing, but we're trying to study how can we change the design or maybe the shape of the bar so that we can better design for smaller cracks. And a good result that we saw, looking at these graphs, the solid line is showing you the spiral bars, and the drift ratio of these spiral bars are very stable, and that's something that we looked at also in design. It's very important to have a stable drift ratio because you don't want your structure to just deform and then break. So it's very important. And this regular bars, although you're able to apply the load to its maximum capacity, but the drift ratio is not very stable. So in conclusion, we concluded that these high spiral bars will exhibit wider cracks, definitely. We're able to see that. But the strength of the concrete is dependent only on the type of bar. So no matter, concrete is a very material, it's very strong when you push on it, but when you pull on it, it's very weak. So the type of bar that you put on concrete will determine the type of cracks and the elongation you get out of it. And also at higher stresses, flexural cracks these flexural cracks that I show you will widen, which is a big problem. And also you'll be able to see these small cracks developing. In concrete also, high-strength spiral bar, they have a stable drift ratio. That's telling us that they're deforming in a stable manner, so we need to work on it better to see how we can change this design and design for better. And these high-strength spiral bar are good because they reduce the congestion. If you look at our concrete is an element that's not going away, in the near future. It's been for the past 100 years, so concrete is going to be around for a long time. So for us, we need to understand that using this bar and the bar that we reinforce concrete with is very important in terms of elongation, in terms of bonding, and reducing labor. So we can use high strength to reduce labor, and that's good for our environment. The future research that's going to be happening is looking at the effect of the yield strength. So how can we study how this bar are elongating so that we can study the cracking behavior of this bar and how it's deflecting inside concrete. And also the anchorage and splash behavior, and dealing with our concrete and columns design, so that because the structure we have columns, we have also beams going. So if we can study how these materials are acting in different concrete frames and columns, it's also important. And the most important that I think is really important is the bond between the high strength bar and the concrete, because concrete and steel are very important. So understanding the bond at this molecular level is very important so that we can continue forward. And I want to thank my mentor, Dr. Wasim Ghanum, and the McNair Scholar Program at UTSA, and also our program director and program manager, Mr. Dura and Ms. Sonia Valencia, and my fellow scholars here in the back. And also I want to thank my family, my father, and my sister Mary, who have been supporting of this project also. And I also want to thank you.